All right, so the goal of this segment is to calculate how far a gas atom will travel before it collides with another gas molecule. And this has a lot to do with the transport properties that you see of gases, including the thermal conductivity, the diffusivity, the viscosity. All of these properties are intimately related to how far an atom travels before it collides with another atom. So how can we do that based on what we already know? Well, if we're using this this model of gases being essentially hard billiard balls that are traveling through space, then what we can do is basically just track the motion of a single atom and pretend like that's all that matters. So here's what I'm going to do. So like I've drawn a couple of atoms that are sitting in this gas here. Imagine that I track the motion of one of these atoms through this gas. And we've already established that, basically I can assign a diameter d to the size of this atom, and I can sort of estimate that based on, let's say, we've already estimated this based on the size that an atom takes up if I had a solid material that was not a gas. So I can estimate what that size d is. And what I'll do is I'll say that, how many is it? What defines whether it collides with another atom? Basically, as this particle travels through space, the real question is, will it encounter anything within an imaginary cylinder that is of diameter 2d, right? So imagine that, if during the travel of our, highlighted molecule, there are any other molecules that are within this imaginary cylinder of diameter 2d, then it will just touch it on the edge. It'll just sort of nip it with the sides of the billiard ball, and so that would create a contact. You might imagine that if the two balls that collide, let me draw an imaginary one that's sort of right on the edge there, that collision might not be all that impactful because it sort of is just nipping it on the edge rather than sort of a full-blown collision. But for the sake of just determining whether a collision happened, I'm just going to highlight this little cylinder here and say that if the ball travels through the cylinder and collides with anything within size diameter 2d, then I'll count that as a collision. So let me just draw that on its side one time. So I'm gonna basically track the motion of this ball as it goes through let's see if I can shift this around a little bit. Basically anything that it encounters within this imaginary cylinder is going to be counted as a collision. So there are potentially a bunch of other little billiard balls that are sitting around here, all moving in their own little directions, potentially. And the question is whether something hits. So the way I'm going to do this, so let's imagine that our billiard ball is moving with speed v. I haven't really talked about what that speed is yet, although we'll come to that in a second. But let's just imagine that it's moving in the direction of the cylinder with speed v, and then that means that this distance must be d. Probably didn't draw that correctly, but this size is also d. And then let's ask, what's the distance that our ball travels before it collides with something? Well, that would be, so one way to do this is to say, well, what is the total distance that you would travel in time delta t? So total distance in time delta t, and then what I'll do is I'll divide that by the number of collisions in time delta t. Okay, well, what's the total distance? That one's easy, right? So that would be, actually, let me shift some of this stuff down to give space. So what's the total distance we travel in time delta t? Well, that would be v times delta t, right? That's the numerator. And then how many collisions would I have in time delta t? Well, let's think about this. How would we calculate that? Well, that is basically the number density of atoms, so the question is how many atoms are in the cylinder that's swept over time delta t. So the volume of that cylinder, so I'll write it this way, so that would be the number density of atoms times the volume swept in time delta t, but the volume swept is pi times d squared divided by, so that would be the area times the distance, v times delta t, right? And of course, these two things cancel in that case, and so it approximately goes as 1 over eta times 1 over pi d squared. Generally, this thing over here, we can sort of generalize this concept of the geometry of this thing has to do with the geometry or the area cross section taken up by our gas. We can generalize this to a non-billiard ball type model by saying that this is 1 over eta times something that I'll call the scattering cross section. So one other thing about that is that the scattering, okay, so in our simple model, the scattering cross-section is pretty easy to see, right? So I'll write this as the scattering cross-section for our simple model. That turns out to be pi times d squared. It turns out that in a marginally more complicated, so what we've done here is we've essentially pretended like the atoms that are being collided with are frozen in space. We're basically just pretending that the number density of atoms is the only thing that matters. The average number density of atoms is the only thing that matters. However, it turns out that what matters is not so much the speed that so we've been working with the speed that our molecule is moving, but it turns out that the speed that matters in the number of collisions per time delta t is not just the speed of your molecule, like it's not just the speed of this molecule, but it's the relative speed of this relative to this. That's what determines the number of collisions in time delta t. And it turns out if you do that calculation a little bit more carefully, I'm not going to do it here, but if you do it a little bit more carefully and account for relative speeds, I'll just write delta relative speeds. It turns out that number turns out to be about square root of pi times d squared. Or sorry, square root 2. Square root 2 of times pi d squared. And so this is sort of the first order correction to that. And then there's a whole separate set of corrections you can do if you want to do this for a Leonard-Jones potential. But for the billiard bulb model, this is what I'm actually going to use on the next page. If you're interested in knowing where this comes from, you can look it up on the internet. I think the Hyperphysics website has a nice summary of how to calculate the mean. This is related to something called the mean free path, or the scattering cross section of gases. I'll just refer you to Hyperphysics for more info. I'll try and leave a link on the Canvas site. But basically, if you just use the relative speed of the two atoms, this will come out naturally. I try not to get too bogged down in the details for that kind of stuff. All right, so what I'm going to do now is I want to actually calculate, so what is that distance for a typical gas? So distance between collisions. All right, so the equation we're going to use is that the mean free path, or the average distance between collisions, is going to be something like 1 over the scattering cross section times 1 over the number density. The number density is P over kBt. And so let's do that for a couple of different conditions because it's kind of interesting. So first let's do this at atmospheric pressure. So that's the most important one. So at normal conditions, that number, so I'll use the conditions for argon, right? So for argon, D was like 0.34 nanometers. So if I do that for argon, you'll see that this turns out to be about 80 nanometers. So now remember that the distance between atoms was actually more like 3.5 nanometers. So 80 nanometers is quite a long distance, sort of a surprisingly long distance, I would say, that something can travel statistically without bumping into something else. So it is quite a different size scale. You know, so if like we're trying to draw these things, you know, if this was supposed to be, so that was supposed to be something like 3 nanometers, or 3 or 4 nanometers was the distance between atoms. That means that on average, this thing can actually go, you know, something like 80 nanometers before it's statistically likely to actually run into another atom. That's quite a long distance. A little surprising, I would say. But anyway, so this is at at atmospheric conditions, the mean free path is something like 80 nanometers. Now, let's use a trick that, okay, so let's suppose that I wanted the gases to have a longer mean free path, or a longer distance between collisions. So one way you might do that is by vacuuming, right? So if I use a vacuum, so I can buy a vacuum pump, like a standard rotary vane or scroll pump. That'll get you to about, typically people who sell pumps do things in a strange unit called torr. So a typical scroll or a rotary vane pump will get you to about 5 millitorr. Or in other words, so in SI units, that would be about 0.2 pascals. So if you do things at normal temperature and you do them under vacuuming conditions, oops, what happened? Then basically you'll calculate a much longer mean free path, right? So using a standard vacuum, you can get that mean free path to be as large as 4 centimeters, which means that if I'm using a pump, if there's a pump that's removing some of the atoms from the gas, then it's obviously possible to make machines and vacuum chambers where the distance between the walls in the chamber are larger than, or are smaller than, the distance between collisions. So in that case, if the gas no longer if the gas is more likely to collide with the wall than it is to collide with the gas, then the properties, like the transport properties of things, no longer depend on the gas itself. They depend on the dimensions of the wall. And so that leads to something called boundary scattering limited transport that we'll talk a lot about. But I'll just point out that for gases, it's possible to get there even with very cheap pumps like rotary vane and scroll pumps. This is what I would call a not very powerful pump. But there are pumps that can actually do a lot better than that. In my own laboratory, I use what's called a turbo pump to remove gases from my deposition chambers. And so these are chambers that are designed to deposit metals and other materials. And in that case, where you're really trying very hard to remove gases, you can get down to like, something like 1 e to the minus 7 torr, and if you turn that into pascals, that would be something like 1 e to the minus 5 pascals. In that case, you can get mean free paths that are measured in close to kilometers. Instead of in centimeters, you can be measuring in kilometers, basically. And so, that would be more like a turbo pump. Again, a turbo pump is not a super rare device. These are common devices, or cryopumps. for some fancier chambers. But you can make the mean free path, or the distance between collisions for atoms, so long that gases are extremely unlikely to actually bump into one another. They're much more likely to bump into the walls of a chamber. Let me do one more slide on this, where I give you an example of like what happens in a typical deposition chamber for evaporation. Let me break the video though.